When you've completed this lesson, you should be able to simplify problems that involve natural and common logarithms. As well, you'll be able to convert exponential equations to logarithmic equations using these tools. Photonics technicians need to use these functions to evaluate formulas, simplify expressions, and we'll be using common logarithms, which are base 10, as well as natural logarithms, which are base e. For example, the transmission of an energy through a thickness x of an absorber of coefficient alpha is defined by the expression I is equal to the incident energy, I sub 0, times e to the minus alpha x. So we'll have to work with expressions just like this as a photonics technician. Here's an example scenario, kind of problem that you may encounter as a photonics technician. A neutral density filter has an optical density rating, OD equals 0.4, between 400 and 700 nanometers of wavelength. So if we have incident helium neon laser light at 632.8 nanometers, how much of that light's going to be transmitted through there? Well, we have a formula, T is equal to 10 to the minus OD power. So we'll have to use power in order to solve that, and some logarithms. Or if we have a thickness of certain absorbing material that's found to transmit 60.6% of the light, and we can use T is equal to e to the minus alpha t to find the absorption coefficient of this material, that alpha value. So we'll return to these kinds of problems after reviewing some of the concepts in this module. You can use algebra skills already to isolate variables. You've learned how to take 3 plus x equals 12 and solve for x. You found that x equals 12 by subtracting 3 from both sides. Or 7x equals 21. You know how to solve for x there. You knew that divide both sides by 7 and you can get x equals 21.7. Or x cubed equals 64. You could solve for x by taking the cube root of both sides. And you find that x is equal to the cube root of 64. But how would you handle something like 3 equals 2 to the x, 2 raised to the x power? How would you isolate the x there? There, it's not simply a division or subtraction or a square root or something that's going to help you. You're going to have to know about logarithms. And that's how we're going to proceed with this lesson here today. Let's look at the powers of 10 and their logs here. See if you can see the pattern. 10 is equal to 10 to the 1 power. And if we take log of 10, the answer is 1. 100 is equal to 10 to the 2 power, right? If we take the log of 100, it equals 2. 1,000 is equal to 10 to the 3 power, and the log of 1,000 is equal to 3. Are you beginning to see the pattern now? 1,000,000 is equal to 10 to the 6th, and if we take the log of 1,000,000, sure enough, we get 6. Going the other direction, if we have a smaller number like 0.1 or a 1/10, that's the same as 1 over 10 or 10 to the minus 1. And the log of 0.1 is negative 1. Sure enough, it still works. The exponent matches. For 0.01 or 100th, that's 10 to the minus 2. And the log of 100th is minus 2. So you can see all the way down the list how that works. So in general, we know that log of 10 raised to the x power is equal to x. Now by the log of 10 to the x equals x, we usually mean the log of base 10 of 10 to the x equals x. We can have different bases. The common log has a base of 10. We can also have logarithms of other bases like base of 2, all right? If 8 is equal to 2 to the 3rd power, then the log base 2 of 8 is the same as the log base 2 of 2 to the 3 power, and that equals 3. So see, the log function can undo the exponent operation. We could have another example of base 2. 512 is equal to 2 to the 9th. So what do you think the log base 2 of 512 will be? Sure enough, it's 9. Or base 16. We have this really large number is equal to 16 to the 5th power. And if we take the log base 16 of that number, it'll be 5, because that's the exponent that's on the base. We could have base 4 numbers. 128 is equal to 4 raised to the 3.5 power. And the log base 4 of 128 equals 3.5. Did you notice something different here with this one? Notice that the result does not always have to be an integer. Here we had an example where it was not an integer. 4 raised to the 3.5 power. If we take the log base 4 of that, sure enough, it comes back as 3.5. It undoes the exponent function. Just like exponents are not always integers, so we need our log function will deal with that. So if we take the log base 10 of 50, well, it's not going to be an integer that's going to give us 50 if we raise 10 to some power. But if we raise 10 to the 1.69897 power, we'll get 50. Or we could have the log base 10 of a square root of 2. And that'll equal 0.150515 approximately, such that if we raised 10 to the 0.150515 power, we would get right back the value for the square root of 2. Let's look at some natural logarithms now. That's not base 10. When you see the log function with no base, you can usually assume that it is the log base 10. But there's a very special base that is known as e, okay, and this is the value that it has approximately rounded to 20 places. It just goes on forever and ever and ever. It's not, does not ever stop, never repeats. It's a very special number called a transcendental number. And you don't need to remember that, but just know that e is a very special number. Instead of log base e, we write instead ln. We can refer to it as the natural logarithm. So if e squared is equal to 7.389, if we take the natural log of 7.389, we get 2. That's the exponent on e. This is just like the log base e. Here's another example. 1,000 is equal e to the 6.90776, and maybe some more numbers there. And we know that because the natural log of 1,000 is equal to 6.90776 with a bunch of other numbers. Now, your scientific calculator is going to come in really handy on this module because you don't know how to calculate logs or exponents without it. So we used to have to look it up in tables, but now we have these little handy-dandy calculators that'll tell us what they are. So to evaluate the log of 1,000 with your calculator, you can do this one in your head. You enter log on a TI-80 series, log 1,000 and enter. On a TI-30 series, you have to type the 1,000 in first and then press the log function. And the answer, of course, comes back as 3. So you can verify that on your calculator. Here's another one to evaluate the natural log then of 1,000. Well, just like before, we'll use the natural log button, then press 1,000 and enter on the TI-80 series. On the TI-30 series, you'll enter the number up first and then the function, just like above. And again, the answer will come back 6.9077 and a bunch of other digits. Let's look at an example. Helium neon lasers with mirrors having reflectivities of 0.99 and an amplifier length of 20 centimeters. We can find the coefficient gain if we use this formula. G is equal to 1 over 2L times the natural log of 1 over R squared. So let's substitute those values into the formula. And there's our 2L. And down here is our 1 over R. And we'll square it. So the first thing we're going to have to do is to square that 1 over 0.99 squared, and we'll get 1.203. And we have 1 over 2 times 20, which is 1 over 40. And the centimeters, we'll pull that 1 over centimeter out over here so it doesn't get mixed up with our calculations. Now we get to use our natural log function on our calculator. So go and do that, and the answer will be 0.000503 per centimeter. Or if we put it in scientific notation, that would be 5.03 times 10 to the minus 4 per centimeter is our gain coefficient. So this laser has a gain of about 5 times 10 to the minus 4 per centimeter. Here's some calculator exercises that the text suggests that you try. So let's just take the log of 143. On the TI-80 series, remember you have to first enter the log function and then enter your number and press enter. On the TI-30 series, you do just the opposite. You put the number in first and then tell it you want the log of that number. And the answer will be 2.1553 with some other digits probably. If we want the natural log of 65, on the TI-80 series, you press the log function, then 65 and enter. Whereas on on the TI-30 series, you're going to go 65 and then the log function, and the answer will be 1.8129. Or if you want to divide two natural logs, this gets a little more complicated. You have to press the natural log function and then tell it you want to take the natural log of 3, and then you have to put a closing parentheses on these TI-80 calculators to tell it to finish doing that and divide it by what comes next. So you divide it by the natural log of 2, and you don't have to put the closing parentheses on the ending one. You just press enter. On the TI-30 series, it's actually a little easier. You just put the number 3 in and hit the natural log, and it evaluates it right away. Then you divide that by 2 and the natural log of that, and it'll perform that operation right away, and then press equals, and it will calculate the division of those two, and your answer will be 1.5849. How about one that we should know the answer for? Log of 10,000. You know what the answer is for that, right? It should be 1, 2, 3, 4 zeros. It should be 4. And for TI-30, you do the 1,000 and then the log, and the answer is 4. How about the natural log of e cubed? You should know what this is as well. This one you're going to have to, on the TI-80 series, you have to work with those parentheses again. You have to press the natural log button. Then you need to get to the e to the x button, and to do that you have to go second e to the x, and that provides an open parentheses for the 3. And then you could press enter right now in this case, or you could close the parentheses for the e to the x and then close the parentheses for the natural log. It's optional. When the parentheses are the very last thing in the expression on a TI-80 series, you can just press enter and it will close them automatically for you. On the TI-30 series, it's much shorter. You just enter 3, second e to the x, and it'll evaluate the e to the cubed, and then you turn around and press the natural log function, and it'll perform that on the value that's in the display. The result will be 3. Now, let's see how we use log to help ourselves with algebra. Just like we used algebra to solve addition and subtraction and multiplication and division problems, now we're going to learn how to use logarithms and exponents. As you know, log of 10 to the x equals x. So if we have some function of f that's equal to 10 to the x and we take the log of it, we can take the log of both sides and we'll end up with the log of 10 to the x, which we now have learned is x. So the log of that function will equal x. So this is a way to get to the x in that expression up above. Similarly, for a function that's a natural log, if we have e to the x and we take the natural log of both sides, natural log of e to the x will be x. And on the other side, we'll have natural log of whatever's on the other side. So if we can have any kind of expression over here that's equal to e to the x, then we can take the natural log of both sides, and this will be that other expression in there, and that will equal x. So in general, for any function f is equal to b to the x, for any base, then we can just take the log of base b of that function f, and that will equal x. That's a powerful thing to remember. You might want to take note of that and circle that in your textbook. Now let's look at example 3. Given that y is equal 10 to the 2x power, let's solve for x. The solution to that is, first, let's reverse our given equation so that we'll have x on the left side. Then we'll take the log base 10 of both sides, just like we saw in the previous slide. Take log of this function, and it equals log of y. The exponent will come down from the base and give us 2x equals log of y. One more step. We'll have to divide both sides by 2, and x will equal log of y divided by 2. How about a second example? Y is equal to e to the minus 3x. We need to solve for x. Again, just reverse the equation so that x is on the left side where we'd like it to end up. And take the log, base e, or the natural log, of both sides. This will, of course, undo the exponent here, and then it'll come down to minus 3x. And on the right side, we've just got the natural log of the variable y. Now we divide both sides by negative 3, and x will equal negative the natural log of y over 3. Let's now look at the solution to the opening scenario. We now are ready to tackle that problem. A neutral density filter has an optical density OD of 0.4 between this wavelength range. What percent of our helium neon light, which is in that range, does that filter transmit? We can use our expression T is equal to 10 to the minus OD power. Well, we substitute the value for OD into the formula. 10 is negative 0.4. That's our OD value. We can evaluate that. It comes out to 0.398 rounded. If we do that on a TI-80 series of calculator, it's 10 raised to the negative 0.4, and then press enter. On a TI-30 series, we have to go 10, and then y to the x power, and tell it what we want x to be. We want it to be 0.4, and then change the sign to negative, and then equals. So it's a little cumbersome dealing with the y to the x function. So the filter transmits 0.398, or about 39.8% of the incident laser beam. And the second part of our opening scenario problem had a thickness T is equal to 5 centimeters of certain absorbing material that was found to transmit 60.6%. And we're going to use T equals e to the minus alpha little t, the thickness, to find the absorption coefficient alpha of this material. So we're looking for alpha in this case. So to solve for that formula for alpha, then substitute values for t and to calculate the value for alpha. So we'll reverse the order like before to get the alpha on the side that we'd like it to be. Take the natural log of both sides, natural log because we're dealing with the base of e this time, and simplify. So we know that the natural log function is going to bring down the exponent to minus alpha t here equals the natural log of t on the right-hand side. Now we need to get the alpha by itself, so we'll divide both sides by negative t, and we're left with alpha is equal to natural log of t divided by t. Now we can substitute in our value of 60.6% or 0.606 for the capital T and our thickness of 5 centimeters and evaluate that expression, and we'll get alpha is equal to 0.10 per centimeter. Now let's look at some practice exercises. We'll not do all of the exercises here. We'll just do a few of them just to give you some confidence that you can continue on and do the rest of them. Exercise 1 asks you to evaluate several of these logs. And can you make a generalization about the log of 10 to the n power? Well, using a TI-80 series calculator, you've already seen how to enter the log of 10 raised to the 0 power would be, enter that, your answer is 0. Log of 10 raised to the 1 power, and you get back 1. Looks like the calculator's working right, doesn't it? Log of 10 raised to the 2 power, and you get 2. And so forth. I don't think we need to do any more. You understand what's going on. And so you can see that the log function undoes the 10 to the x function. So in general, the log of base 10 of 10 to the n power equals n. It pulls the exponent down from the 10. Exercise 3 presents you with the optical density problem. We looked at that OD earlier. The optical density of all these light filters and goggles that you wear in the laser lab and so forth are defined in terms of their transmittance. OD is equal to negative log of T. So we can find the OD. Instead of being given the OD, we can find the optical density of a certain glass if we measure that it transmits 1% of the light. So we substitute the value for T and evaluate it. What is the negative log of 0.01? On the TI-80 calculator, you have to press change sign, negative log 0.01, and press enter, and you'll get your result. On the TI-30 series, you enter the value first, 0.01, and then press log, and then change the sign to make it positive, actually, and OD will equal 2. So this glass has an optical density of 2. But you probably knew that already, right? This is a log of 100th, 10 to the minus 2. Exercise 4 asks you to find the absorption coefficient of a laser that propagates it with a transmittance of t is equal to 0.53 through 4.5 centimeters of absorbing medium. Using this formula, alpha is equal to negative natural log of t divided by x. So we'll substitute the values of t and x and evaluate our expression for alpha. Alpha is equal to natural log of t is 0.53 and x is 4.5, and the result is alpha is 0.14. We can see how that happens easily on a TI-80 calculator, just like in the previous problem, except this time we have to append the divide by 4.5 on there. And similarly on the TI-30 series, you enter the number, the contents of the natural log first, then operate on it with the natural log function, and then divide it by 4.5. Oh yeah, and change the sign, and then press equals. So this medium has an absorption coefficient of alpha equals 0.14 per centimeter. Exercise 5 says, if you're given y is equal to e to the 10x, solve for x. To get at the exponent, you know what to do. Take the natural logarithm of both sides, since the base of our exponent is e. So we'll take natural log of y on the left and natural log of e to the 10x. And simplify, and we know that the 10x will come out of the exponent now and be by itself. And we'll divide both sides by 10. So natural log of y over 10 equals x. So x equals natural log of y over 10. And that concludes our treatment of exponents and logarithms for Mathematics for Photonics technicians. I hope you'll have the confidence now to go back and finish all those practice exercises, and you'll be ready to work with algebraic expressions that include both powers and roots and exponents and logarithms. All right, have a good day, and we'll see you next time.